Greetings. I continue with the problem of the supersonic wind tunnel, and you see, it's very ideal if we have a wind tunnel where subsonic flow enters the tunnel, reaches sonic velocities, then continues to supersonic velocities, and then slows down to sonic velocity, and then goes subsonic, and then goes up. That's a very ideal case. But as you know from the shockwave theory and the shockwave in the diverging section of a converging diverging nozzle, after the throat reaches Mach 1, by any further reduction of the pressure downstream, there would be a shock wave after the throat. So there would be a shock wave at here, and then a shock wave at here, and then a shock wave at here, and then there would be a shock wave at any of these stations, okay? And by reducing the pressure downstream, the shock would move down, okay? The shock impact would be sucked down, and then it would come to a test section and would stand somewhere here. So when such a wind tunnel started, there would be a shock wave here. And of course, it's ideal if this shock is swallowed out. Like it was disgorged from here, and we had isotropic flow. But there are points in it that you have to take care of. Let's see what happens if there is a point 1 here, and there's a shock wave, and after the shock wave, which the entry Mach number to the shock wave is 1.8. What happens after this shock wave? So what we have is that we have a flow where its Mach number is m equals 1.8. There is a shock wave, and we move to station 2. And let's calculate the properties for station 2. Well, normal shock tables are almost in every gas dynamics book, and there are also many thermodynamics books which cover compressible flow, also present a table for shock waves and isentropic flow. The isentropic flow table we just used now, we have to use the shock wave table. And what we have in the shock wave table are, of course, a table where equations are here. You see, equations are here. All equations are given values for Mach number MA1, and once Mach number before the shock wave is known, then the rest of the properties follow. Now, our shock wave occurs at 1.8, and therefore the Mach number after the shock is 0.6165. The static pressure ratio is 3.6. Density ratio is 2.3. Static temperature ratio is 1.5316, and the total pressure ratio is 0.8127. Well, I just moved those values into paper, and what no table tells you is that the ratio between total temperatures is 1, and the total temperatures are equal. You should know that. But if you know that M1 equals 1.8, they tell you that M2 equals 0.6162. This is the static pressure ratio, and since we know the static pressure at point 1 at m equals 1.8, we already calculated it. We conclude that P2, static pressure after the shock, equals 3.6133 times 17.40, and that equals 62.87 kilopascals. You see, shock waves, it's important to note that shock waves are excellent means to increase pressure. You see, a compressor with pressure issue of 3.6 would be a large compressor and a very good performing compressor. It certainly should be a multi-stage axial compressor or a centrifugal compressor. But that's not necessarily here. Just a shock wave with minimum thickness would produce such a pressure ratio, and that's an excellent achievement which is quite used in industry. Now, T2, the temperature after the shock wave, T2 equals 1.5316 times the temperature before the shock, which was 182.04, and that equals 278.81 Kelvin. That's the static temperature after the shock wave. And the very important point is the total pressure after the shock wave, and that gives us that PO2 equals 0.8127 times the total pressure before the shock, which was 100 kilopascal, and that equals 81.27 kilopascal. So these are all our values for different properties, and it's a good job if we show all these values on the TS diagram. Well, let's see what these values mean on the TS diagram. You see, what we know is that PO2 is 81.27. This was 100. So let's say that this one, PO2, equals 81.27 kilopascal. This is the point O2, the stagnation point. After the shock is where TO1 equals TO2, the total temperature doesn't change since the shock is adiabatic, but the shock is not reversible, and therefore the total pressure drops, and point O2 is here. Also, we have learned about T2, which is 278.81. So it should be somewhere between this one and this one. It's somewhere here. This is the temperature at 4.2. This is, let's write it here, T2 equals 278.81. So, as you expected, it's in the subsonic range. After the shock, point 2 is in the subsonic range. And you see here, there's an isentropic relation between the total pressure and the static pressure at point 2. So the P2 62.87. 62, this is 0.87 kilopascal. This is P2, and therefore this is 0.2. This was 0.1, and that is 0.2. And if you want to show the shock wave on the TS diagram, then we could just connect 1, 2, 2. And this is the shock wave over the TS diagram. There are also other points at other properties at point 2 that we could calculate. Let's start with A2, which is the speed of sound at point 2, and that equals square root of 1.4 gamma times R, which is 287, and times T at point 2, which we calculated it to be 278.81, and the outcome is 334.7 meters per second. That is A2. We could also calculate V2. V2 equals A2 times M2, and that is 334.7 times 0.6165. You see, we learned from the table that the Mach number after the shock wave is 0.6165, and the outcome is 206.34 meters per second. We could also have calculated V2 from the equation. V2 equals the square root of 2 Cp0 times TO2 minus T2. Inserted values for it in this equation. Very simple as we did before, and check if it gives us the same value, which is, of course, it would. We could do it as a practice at home. We could also put these values in our table. You see, for point 2, the stagnation properties are 300 Kelvin uh, for the temperature and 81.27 for the stagnation pressure. Now, of course, diameter for stagnation is irrelevant. Mach number for stagnation is 0, of course. That's no point for it. That's the definition of the stagnation properties, where velocity and Mach number are 0. The speed of sound, since the total temperature is 300 Kelvin, the speed of sound would also be the same as before. It is the same as before, 347.2. And also the mass flow rate would be meaningless since the velocity is 0. There would be no mass. In fact, there is negligible velocity, and therefore it's not possible to calculate the mass flow rate. Now, the pressure and temperature at point 2, we did find them to be 62.87 was the pressure, and we showed it on the TS diagram. You see, on the TS diagram, we showed it to be 62.87. The temperature, we showed it to be 278.81. The diameter at point 2, well, the shock wave doesn't change the diameter, so the diameter would be exactly the same as point 1. It would be 0.25 meters. Mach number, well, Mach number has changed after the shock, and before the shock it was 1.8. After the shock it is 0.6165. The velocity, we just calculated it to be 206.344, and the speed of sound, well, with the knowledge of temperature, static temperature, we also calculated 334.7, and the mass flow rate remained unchanged, and this is still 7.96. As you remember, when we calculated the throat area for the nozzle, our knowledge was the total pressure and the total temperature and the Mach number at the test section. Now, For the diffuser, conditions have now changed. Before the shockwave occurred, all the truths along the line would be the same. But now, as the shockwave has occurred, then conditions have changed. The total temperature has remained the same, but the total pressure has changed after the shock, and therefore static values have changed, and also the Mach number here has changed. So if we want to calculate the truth for these conditions, then that would be a different truth that we have to calculate that truth as well. Now, for the second truth here, you see uh, the total temperature is the same, and therefore the temperature at the throat would be the same. This is our point 2, this is our point 2, and therefore any throat for point 2 would be along the isentropic line, and therefore this point would be point star, point 2 star, and this line is P2 star. Okay, this was P1 star, and this is P2 star. And if we want to calculate a truth for point 2, we need to uh, calculate P2 star and see what that value uh, would be and what the area of the second truth would be. Well, one way for calculating P2 star, P2 star, is to use the equation that P2 star over PO2 equals 0.5283, just like before, and just multiply that with PO2, which now has a different value. It's 80.27, and calculate the whatever the P2 star is. That we can do that. P2 star would be 0.5283 and times PO2, which is 81.27, and the outcome is 42.93 kilo Pascal. We could also have done the same, it's the same practice. I mean, we just could have just used the equation where this number is calculated from and say that PO2, P2 star equals PO2 times T star, which is 250 for both 1 and 2 divided by TO, which is the same. And this is why this number is the same, because for both um, cases, TO is the same, therefore T star is the same, and this equation should give us the same ratio, which is this one. Then the power is gamma over gamma minus 1, and this would give us the same value. Still, the what we need to calculate is the diameter of the second throat, and to calculate the diameter of the second throat, the equations it require is that whatever mass flow that goes through this tunnel, the first throat here, would also go through the second throat. So if we write the mass flow rate, we would find the correct diameter that mass flow rate would go through it. So the equation for us is m dot equals P2 star divided by R2 R. Well, R is the same, 2 T2 star times P D2 star squared over 4, which is the diameter of the second throat, times velocity, which is V at the second throat. And it's the same as before, because it's 316, because the Mach number is 1, and T star is as before, and therefore V star is as before. And therefore, D star, D2 star, which is the diameter of the second throat when the shock wave is present, would be the square root of 7.961 times 4 times 0.287 and times 250 and divided by 42.93 times P times 316.94. And the outcome for D2 star would be 0.2312 meters. Now, we could put these values in our table, and if you go to this column of our table and see what the values are, we see that the pressure is 42.93, the temperature at the throat is 250, just the same as the first throat. Since the total temperature is the same, the static temperature at the throat would be the same. The diameter is 0.2312, and it's a good job to remember that the first throat had the diameter 0.284, and the test section diameter was 25 centimeters. So this is not that smaller than the test section diameter. Mach number, of course, at the second throat is 1, velocities are known, and mass flow rate is the same. Now, what I want to do is to compare these three diameters and make some conclusions here. Well, let's compare what we have gained for these diameters. You see, the test section diameter was 25 centimeters. Okay, that's fixed, no change. Now, we need a throat diameter of 20.84 for the first throat, so that here there would be a Mach 1 velocity, and this Mach 1 velocity would produce a Mach 1.8 at 25 centimeter diameter. These are fixed values. But the second throat is interesting, because if there was to be continuous increase and then continuous decreases velocity, everything isentropic, the second throat had to be, just like the first throat, 20.84 in diameter. That is centimeters. Now, we learned that to start the tunnel, to get it going in the first place, there would be a shock wave here. And just to allow for the shock, and this diameter had to be 23 centimeters. If it was less than 23 centimeters, the shock would never come to the test section and would stand somewhere in the diverging part of the nozzle, and the second throat would choke, and nothing more would happen. So the minimum diameter we need at the second throat, just for let the shock wave to come to the test section, and then of course it would be swallowed out, then it has to be 23.12 centimeters. That's the point. So if this is a fixed geometry wind tunnel, this second throat had to be 23.12 just to let the shock wave go through. And if this is 23.12, what we would learn is that the flow would start at 0, it comes to 1, it comes to 1.8, and if it goes isentropically through this throat, then the value of the Mach number at the second throat would be 1.58 and not 1. And therefore, you would have supersonic velocity throughout. A very good question is that if we have a shock wave here, but if you want to reduce the velocity to subsonic values, okay, we have a shock wave here, it is subsonic. Then why at all do we need the converging, diverging, also diffuser after the test section? And that's the true question. And in many real wind tunnels, up to Mach numbers 3 or 4, they don't bother with such a supersonic diffuser, and the total pressure drop would not be would not be prohibitive. So it would be still very good to accept this total pressure drop and get away with the supersonic diffuser and just reduce velocity with a normal shock wave. Normal shock waves are very important means for um, increasing static pressures. They are very important in increasing static pressure. They are used in compressors, at least very, very, very important, and very airplane, in many airplane intakes. So, and this is why it happens, and supersonic wind tunnels are good means to test them. Well, thank you very much for watching, and cheers.